Hello everybody, and welcome to our video on derivatives involving inverse functions. So first, let's recall the two equivalent definitions of an inverse function. Definition 1, if f is 1 to 1, then y equals f of x if and only if x equals f inverse of y. In other words, the x and y values, the inputs and outputs, switch between the inverse functions. And definition 2, if f is 1 to 1, then f inverse is the function that satisfies both f of f inverse of x equals x and f inverse of f of x equals x. So in other words, when you compose inverse functions, you get your input back. And of course, we've dealt with this quite a bit, dealing with logarithmic functions, which are the inverses of exponentials. So now we want to figure out, okay, how do inverses affect our derivatives? So first, let's just note a little theorem that we're not going to prove, but it can be proven using the definitions of continuity and the limit definition. So if f is a one-to-one function and continuous, then the inverse of f is also continuous. So example 1, find the inverse of f of x equals x cubed using definition 1, and then confirm that it is the inverse using definition 2. Then find f prime of 2 and f inverse prime of 8. So let's go ahead and do that. So definition 1 says you switch inputs and outputs. So for the function f, we'll write this as y equals x cubed, which means f inverse of x. I would switch my input and output, x equals y cubed, and then take the cubed root to solve back for y. So the inverse function is y equals the cubed root of x. So that's the first part of the question. Now let's check that these inverses are inverses using definition 2. In other words, we're using the other definition to make sure we didn't make a mistake. So if I take f of f inverse of x, what that means is replace the input of f with the entire function f inverse here. So I take x cubed and replace the x with the cubed root of x, but we know that the cubed root of x cubed is x. Likewise, f inverse of f of x would be taking the cubed root of x and replacing the x with x cubed, which of course also gives us x. So there, we confirmed that it is the inverse. So now we're going to do two things. We're going to find f prime of 2, and then the inverse derivative at 8. So f prime of x is just 3x squared. So f prime of 2 is 3 times 4, which is 12. Now you may ask why I picked these values. Well, here my input is 2 for the original function, which gives me 8. So for the inverse function, I'm using the output of f, and I'm checking the derivative at that output. Okay, so now when I take a look at the inverse function, and I take its derivative at x, so remember this is the cubed root of x is the same thing as x to the 1/3 power. So I get 1/3 x to the negative 2/3 power, which is 1/3 times the cubed root of x squared. So now if I want to evaluate the inverse derivative at 8, that's 1/3 times the cubed root of 8 squared. Now, 8 squared is 64, and we could look for the cubed root of that. Well, what would the cubed root of 64 be? Well, 4 times 4 is 16, times 4 is 64. So we could redo this as 1/3 times the cubed root of 64. So that's 1/3 times 4, which is 1/12. So what do we see here? When we took the inverse derivative at 8, the output of the original function, to the corresponding input, the derivative we got was the reciprocal of that corresponding derivative for the original function. So that should be very, very interesting. Now, let's go ahead and take a look at a picture, and it becomes a little more obvious why this happens. Okay, so here we've got two graphs, the graph of f in blue and the graph of f inverse in red. And so what I've drawn here is the tangent lines on each function. Now, remember, f and f inverse reflect over the line y equals x. That's this green line in the middle. It's y equals x. So these are reflections over that line. And so if I look at the point BA on the function f, the corresponding point is AB on the function f inverse. And so when I look at the slopes here, the rise is delta y for the slope formed on the f function's tangent, and the run is delta x. But when I take that same tangent line and I move it over the reflection, the image of this triangle reflects as well. So we see that the rise here is delta y and over delta x. So what do we see? Well, these are the reciprocals, rise over run versus the rise over run, right? The delta y and delta x have flipped sides. The long side has switched places on each of these triangles. So in other words, f inverse prime at A is delta y over delta x, which is 1 over delta x delta y, which is 1 over f prime of B. So you get the reciprocal of the slope here. And since f inverse of A equals B, right, the output was A, so the input is B, and you flip them around for the inverse function, we can rewrite this as f inverse prime of A equals 1 over f prime of f inverse of A. Okay, so that's not a rigorous proof, it's just a geometric justification. So we're going to go ahead and look at the rigorous proof here. If f is a one-to-one differentiable function with inverse function f inverse and f prime of f inverse of A is not 0, then the inverse function is differentiable at A and f inverse prime at A equals 1 over f prime of f inverse of A. Proof. So by definition, we write f inverse prime of A is the limit as x goes to A of f inverse of x minus f inverse of A over x minus A. So if we let f of B equal A, right, so we're just choosing that notation that B is the input that corresponds to the output A, then that would mean f inverse of A is B, and we let y equals f inverse of x, so we switch inputs and outputs, x would be equal to f of y. So we can make these substitutions into our definition of the derivative, and f inverse of x becomes written as y. F inverse of A becomes written as B. F of y replaces x, and f of B replaces A. Now, I've written this still as the limit as x goes to A, but we should note that this is equivalent to saying the same thing when y goes to B. And if x is approaching A here, y is also going to be approaching B. So this limit is still equivalent. It's acting on the same behavior. So in any case, if I have y minus b over f of y minus f of b, I take the reciprocal and write that as 1 over f of y minus f of b over y minus b. Those are the same thing. 1 over this is the same thing as this. And I know that I can move limits inside of the quotient, right? So this is 1 over the limit as x goes to a of this expression. But again, this expression, once again, that's equivalent to y going to b. This expression is the derivative of f at b. So we can rewrite that as 1 over f prime times 1 over f prime of, not times, of f inverse of a. Now, we used a and b here just because we had multiple variables to work with, and so we were imagining a single fixed point and looking at the derivative at that fixed point. But of course, we can rewrite this final expression by substituting x in place of a. That doesn't change anything. And that leads us to the following expression, that f inverse prime of x equals 1 over f prime of f inverse of x. So with that, we can apply this fact to evaluate some derivatives of inverse functions. So here, I have f of x equals 2x plus 1 plus sine of x. Now, if I tried to solve for f inverse, this would actually be very hard to solve for, because when I switch inputs and outputs, I'd have sine of y, 2y plus 1 plus sine of y, and I have no way to break that y out of the sine function, so to speak. But I do know it has an inverse. This is a one-to-one function. I'll just tell you that. I'm not gonna go through the proof of that. But this is a one-to-one function, and it has an inverse. So since we know that it's one-to-one and has an inverse, that inverse should be differentiable. Okay, so how do we find it? Well, f inverse prime of 1. Well, what is f inverse prime of 1? Should be 1 over f inverse, or f prime of f inverse of 1. But that means I need to first know what's this value, f inverse of 1. So that's the same thing as asking what's the x value that gives me 1 from my original function. Oh, well, when I look at this, if I plug in 0, I get 0 plus 1 plus 0. So f of 0 equals 1. So f inverse of 1 equals 0. Okay, so that's good. So now, really what I'm asking for is 1 over f prime of 0. Okay, well, what's f prime? Well, f prime of x is just 2 plus 0 plus cosine of x. So 2 plus cosine of x. And so f prime of 0 is just 2 plus cosine of 0, and cosine of 0 is 1, so this is 3. So altogether, this derivative for the inverse function is 1/3. Okay, so let's go ahead and move on, and we're going to take this idea and make it a little more powerful. We're going to first find the derivative for logarithms, which we won't need the inverse derivative rule yet for, but you'll see how that's going to tie into this shortly. So, theorem, the derivative rule for logarithms. The logarithmic function f of x equal to log base a of x, where a is positive, and I should have also included in here not equal to 1, is differentiable, and the derivative with respect to x of log base a of x is 1 over x times log base a of e. So that kind of seems like a strange derivative rule. So let's go ahead and go through the proof. So f prime of x equals the limit as h goes to 0 of, this is f of x plus h minus f of x over h. That's our derivative definition. Now here, log base a of x plus h minus log base a of x is log base a of x plus h over x. That's just the quotient rule for logarithms. So this is the quotient. This is not a derivative rule. This is the quotient rule for logs. And now instead of writing this as divided by h, I'm just going to rewrite it as 1 over h times log base a of 1 plus h over x. And then this is a constant multiple in front of the logarithm, and we can use our log constant multiple rule, or we also refer to that as the log power rule. So the power rule for logs. Again, this is not a derivative power rule. We're referring to it's the power rule for logs that says you can take this constant multiple and move it into the exponent position here. And hopefully, this expression inside the logarithm looks kind of familiar. It should look a lot like our definition of e, but it's not quite right. That definition of e would have 1 plus h to the 1 over h instead of 1 plus h over x. So it's not quite right. So what we're going to do is make a substitution here. And the substitution we're going to make is letting z equal h over x. And so when we substitute h over x, we get z. And then for 1 over h, well, if I have z as h over x, then z times x is equal to h. So I plug in that and I get 1 over xz. And now instead of 1 over x times 1 over z, we're rewriting this using our exponent laws. So this is 1 plus z to the 1 over z to the 1 over x power. So now we have this power here, and we're going to use our power rule for logs again and move this power in front of the logarithm. So we get the limit as z goes to 0 of 1 over x times log base a of 1 plus z to the 1 over z power. And then we use the continuity and convergence theorem from back in the old limit times to move that limit inside the log function. So we get 1 over x times log base a of this limit. And this limit is by definition e. So this is 1 over x times log base a of e. Okay, so that's how we get the derivative rule for logarithms. Now there's one logarithmic rule we're going to use way more than all the others, and that's the natural logarithm. So the derivative of the natural log would be 1 over x times log base e of e, because e is the base for the natural log. But log base e of e is just 1. So this is just 1 over x. So in other words, ln of x prime is just 1 over x. So if you're looking at the natural logarithm, you've got a much simpler derivative here. So just keep that in mind. All right. So moving on, let's go ahead and tackle a problem with this. Evaluate the derivatives of the following functions. F of x equals log base 3 of x. So log base 3 of x prime is just 1 over x times log base a of e. But what's my base a? It's 3 in this case. Okay, that's it. That's the derivative for that one. Let's move on to the next. Okay, we've got the derivative with respect to x of 7 times ln of x. So I pull out my constant multiple, and then I take the derivative of the natural log. That's 1 over x. So this is just 7 over x. Okay, well that's it for those ones. Now let's tackle the derivative rule for exponential functions. So this is where that inverse theorem came into play. So the exponential function f of x equals a to the x for a greater than 0 and a not equal to 1, should have also been in there, is differentiable, and the derivative with respect to x of a to the x is a to the x times ln of a. So how do we get that? Well, the derivative of a to the x with respect to x is 1 over f prime of f inverse of x. That's our inverse derivative rule. But that's the same thing as saying 1 over f prime of a to the x. So I know what f prime of if this is my inverse function. So keep in mind here, we're thinking of a to the x as the inverse and the other function as the log, right? So the derivative of this log is, of course, 1 over x times log base a of e. So here, when I take this derivative, I get 1 over a to the x. I'm replacing a to the x in my x. I'm replacing x in my function with a to the x times log base a of e. So I move the a up top. And then here, I'm just using the change of base formula to rewrite this as ln of log base a of e as ln of e over ln of a. And then I'm multiplying by the reciprocal. But when I multiply by the reciprocal, ln of e is 1, so I don't need it anymore. So in other words, the derivative of a to the x is a to the x times ln of a. Now, when a is equal to e, we get the special case. The derivative of e to the x with respect to x is just e to the x. So when you take the derivative of the exponential function base e, it just gives back itself, e to the x. That should make sense when you look here. You would get e to the x times ln of e, and ln of e again is just 1. So we get a nice simple derivative formula for e to the x. Okay, so again, when we take the derivative of f of x equal to 4 to the x, 4 to the x prime equals 4 to the x times ln of that base 4, which is, boom, that's the whole thing. Okay, and so now when we do the derivative of cosine of x plus e to the x, we apply the sum rule, and the derivative of cosine is negative sine of x, plus the derivative of e to the x, which is just e to the x. Done. Okay, so let's go ahead and move along. So now we're going to look at some more inverse functions. So here we're going to look at the derivative rule for inverse sine. So the trigonometric functions are not typically invertible, or they're not actually invertible because they're not one-to-one functions. So when I draw the graph for sine of x, the Cartesian graph, it looks roughly like this, right? We're going to do a quick sketch of this thing. Alright, so this is the graph for sine of x. But what's the problem? The problem is that this is not one-to-one. So that's why we put artificial restrictions on our trigonometric functions when we want to have inverses. So if I just cut this here and here, now it's one-to-one. It passes what we call the horizontal line test. In other words, each output only has one corresponding input. Okay, so now we put this restriction in place, and that's why this is listed here. For x between negative pi over 2 and pi over 2, f of x equal to sine of x has an inverse, sine inverse of x, which is differentiable, and the derivative of sine inverse of x with respect to x equals 1 over the square root of 1 minus x squared for x between negative 1 and 1. Obviously, we can't divide by 0 here. So proof. Well, the proof is pretty straightforward. The derivative of sine inverse of x with respect to x is 1 over f prime f inverse of x. So I plug f inverse of x in, that's sine inverse of x. So this is 1 over cosine of sine inverse of x. So f prime being the derivative of sine, right? If f inverse is sine inverse of x, f is sine, the derivative of sine is cosine, so we're taking cosine of sine inverse of x. So now if I go over here, we're gonna pause for a moment, and we're gonna look over here. So sine inverse of x, the output of that is an angle. So correspondingly, x equals sine of theta. We're gonna call theta sine inverse of x. So if theta is sine inverse of x, then x over 1 is sine of theta, and I can draw a corresponding triangle with my opposite x and hypotenuse 1, and then I need to solve for z, this adjacent side. And that's the Pythagorean theorem. I just go z squared plus x squared equals 1. Then subtract the x squared, that's 1 minus x squared is z squared. And so take the square root, and I get z equals the square root of 1 minus x squared. Now I only have to look at the positive square root here because of the restriction on x. I'm only going to get positive values for cosine here. Okay, so with that being said, that means cosine of theta is the square root of 1 minus x squared. And this is theta. Theta is sine inverse of x. So 1 over cosine of theta equals 1 over the square root of 1 minus x squared. So that one's maybe a little tougher just because we got to take this little detour through the trigonometry land. Let's go ahead and look at one more, and we're going to apply the same idea. So the derivative rule for inverse tangent. So again, back in pre-calculus times, we saw that in order to have an inverse, we restricted tangent of x to x being between negative pi over 2 and pi over 2. And then tangent inverse of x is differentiable, and its derivative is given by 1 over 1 plus x squared. So the proof is basically the same. The derivative of tangent inverse of x with respect to x is 1 over f prime of f inverse of x. F inverse of x is tangent inverse of x. The derivative of tangent is secant squared. So this is 1 over secant squared times tangent inverse of x. I'm going to treat tangent inverse of x as an angle theta. So x equals tangent of theta, or x over 1. That's opposite over adjacent. Solve for z. 1 squared plus x squared equals z squared. Z is the square root of 1 plus x squared. So secant of theta is my adjacent, my hypotenuse over my adjacent, which gives me the square root of 1 plus x squared. So if I had plugged in 1 over the square root squared, I just get 1 over 1 plus x squared. Okay, so that's the derivative rule for inverse tangent. Now we got a whole bunch of inverse trig functions, so we're going to list out all of their derivatives here. We're not going to prove all of them. But you will see, similar to the patterns that you saw with the derivatives of the regular trig functions, there are similar patterns with the derivatives for inverse trig functions. Let's take a look. Sine inverse of x, the derivative is 1 over the square root of 1 minus x squared. Cosine inverse of x has the same derivative but negative. Tangent inverse of x has the derivative 1 over 1 plus x squared. Cotangent inverse of x has the same derivative but negative. Secant inverse of x has the derivative 1 over x times the square root of x squared minus 1. And cosecant inverse of x is the same except negative. So that should make it a little bit easier. If you memorize sine, tangent, and secant, and you get those down really well, then all you got to do for the cofunctions, the corresponding cofunctions, is just make them negative. Okay, so y prime here for this part A is just going to be the derivative of 4. I'll switch back to blue here. Of 4 times cotangent inverse of t plus t squared. So this is that's the sum rule, and then we've got the constant multiple, that's 4 times, and the derivative of cotangent inverse of t is just negative 1 over 1 plus x squared. 1 plus t squared, because we're taking a derivative with respect to t, plus 2t. So this is negative 4 over 1 plus t squared plus 2t. Now we've got negative 15 times secant inverse of x. Well, then the derivative for g prime, it's a constant multiple of the derivative for secant inverse, which is 1 over x times the square root of x squared minus 1. And I can just write that as negative 15 over that thing. Okay, now we're on to the derivative for x squared times cosine inverse of x. So we write out our product rule, x squared prime times cosine inverse of x plus x squared times cosine inverse of x prime. That's 2x times cosine inverse of x plus x squared times a negative 1 over the square root of 1 minus x squared. And so we can simplify that slightly, or not really simplify so much as just clean it up a little bit. And instead of x squared times -1, we can write negative x squared over the square root of 1 minus x squared. Okay, that's it for that example. Let's take a look at this one down here. E to the x over sine inverse of x. So we know that the derivative of e to the x is e to the x. We know the derivative of sine inverse of x is 1 over the square root of 1 plus x squared. So we're going to need both of those derivatives. Okay, now it's working for no reason. That doesn't make any sense. Sorry about that, everyone. Word is a strange program. Okay, we need to apply the quotient rule. So we need low d high minus high d low over low squared. This is sine inverse of x times e to the x minus e to the x times 1 over the square root of 1 minus x squared divided by the denominator sine inverse of x squared. I can't do a whole lot here to simplify this, but I can factor e to the x out and write the top as sine inverse of x minus 1 over the square root of 1 minus x squared all over the sine inverse of x all squared. That looks a little better to me, but isn't necessary. Okay, well, that's it. That's our final example. Thanks for sticking around. Have a great day.